All right, let's do a projectile motion problem. So let's say we've got, that's a great way to start. Let's say we've got the ground here, just flat ground for this. And we're going to launch something at, let's say, 60 degrees at a velocity v. Now you like I, okay? So vi equal to 100 meters per second. 100 meters per second is about 224 miles per hour. So, a couple questions. One is, well, what kind of path is it going to take? So it's going to immediately start to, the angle is immediately going to start to get shallower, right? Because we've got a acceleration downward and no other acceleration. So it's going to follow that parabolic arc, of course, and my drawings always get blunted on the other end, but unless there's air resistance, it really shouldn't be. It should be a proper parabola, where this angle right here at impact is also going to be 60 degrees. That angle right there should be 60 degrees. If it is blunted the way I drew it, that would indicate that there's air resistance. And it's still kind of blunted, I think. But that's okay. So we're going to find this maximum height, capital H. We'll find this distance, R, the range. I'm going to give you a special equation for that. We will find, what else should we find? We'll find the time in the air. And I think that'll probably do it for this problem. And then we'll see how some of these variables would change if, say, we went to the moon or something like that. So what are our equations? So in the vertical direction, the y direction, we've got that velocity in the y direction is equal to negative gt plus vy I, and vector. I'm not going to put a vector on the g because while gravity is or does represent acceleration due to gravity, which is a vector, that negative takes care of the direction because I'm taking up as a positive direction. A lot of times in problems that involve gravity, especially if you're just talking about something free falling, we take down to be the positive direction, in which case we don't put the negative there. In that case, our initial y velocity would actually be negative because it's upwards. That's often convenient in problems like this, but in this case, I don't think that's the way to go. And then what else do we have? We've got delta y equals negative g over 2. Sorry if my g's look like 2's. I've been criticized for that in the past. Hopefully you can tell the difference. Vyi t naught squared. And then we've got delta y equals vy squared minus vyi squared over negative 2g. Again, like I said before during our last session, this equation is often written solved for vy squared or just v squared, but this is the way I write it. And then this equation is typically not given to you at all. You get this equation from combining these equations in all kinds of ways. 1/2 vy plus vyi times t. So those are our vertical equations. Are you going to ever get marked wrong if you don't put vector symbols on these things? No, I've never encountered a situation where a grader would mark you wrong for not putting the vectors. I'm just putting them on here for you. And then the x direction, of course, we've got our delta x equals vxt. Okay, so now if we draw the initial vector vi, and we can break it down or decompose it into vx. And I'm not going to put an initial on the x velocity because it's constant. That never changes. So the initial is the same as the value here, 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 here. So I'm just going to call it vx. That's going to be vi times the, well, if that's theta, times the cosine of theta because it's adjacent to the angle. And then vyi, here I do need the I because this is only the initial y velocity, is going to be equal to vi sine of theta. And these are vectors, but okay, fine. Vector. Now these are all, you have to decide what the sign is going to be for these. It's not going to come out just from this stuff necessarily, depending on how you do your angles. So here I know that's going to be positive, and I know that's going to be positive because it's going to the right, which, since I haven't said anything about my horizontal directions, right is assumed to be positive, and I did say up is positive, and this is up, so that's going to be positive. So of course that's going to be 100 times the cosine of 60. Cosine of 60 is about 0.86. 0.866, right? Let's make sure. So 100 cosine of 60. I'm a stupid. That's the sine of 60. Oh no. Cosine of 60 is 1/2. I got my unit circle wrong there. So that's meters per second, and then this one will be about 0.866. So sine of 60, 86.6 meters per second. And this is precisely 1/2 for cosine of 60, so that is 50 meters per second. I really shouldn't even put the squiggly on there. So now we've got those. We can now plug all kinds of things into our equations. So let's do height first. Let's find the maximum height. So maximum height is going to be achieved when we're at the maximum height, which is when vertical velocity is going to be 0. Vertical velocity decreases as you go up, and then it increases as you go down. In order for it to go from positive, by it I mean vertical velocity, in order for vertical velocity to go from upward to downward, it must go through 0. And that happens at the top. So this is going to happen when Vy is equal to 0. And h would be equal to delta y at that location, right? This is going to be equal to delta y at that specific spot. Delta y is a generalized variable that can apply to here or here or here or here or here or here or anywhere. H is that specific one. Capital H is that specific one. You might use lowercase h for height in general at any location instead of delta y. And that's going to be equal to v y squared minus v yi squared over negative 2g. So I don't even care in this case about the horizontal motion. This is just as if we've thrown a ball up at 86.6 meters per second. By the way, if you can do that, you don't need to go to college. You can just go right into Major League Baseball and make more money than anyone ever, because you will be able to, no one will ever be able to hit a ball you throw. So what are we going to do? Okay, so that's going to be 0. All right, so we're going to get, and that negative is going to cancel out with that negative. So we're going to get 86.6 squared divided by 19.6, because g is 9.8 times 2 is 19.6. So we're going to take that number, square it, and then divide by 19.6. Notice in my calculator, I am not doing 86.6, I'm doing 86.6025. And then all the extra decimals too. And that is approximately 382.65 meters. This is a little bit excessively precise if you're dealing with sig figs and all that stuff. I'm not going to worry about that here. I like to go to the 100th of a meter because that's centimeters, and that's a normal unit to use. However, for this, really, you should probably say, actually, if you're doing proper sig figs, it's only a 1 sig fig problem. You should say 400 meters because that's just 1 sig fig, and that's just 1 sig fig. To make it a greater sig fig problem, I could put decimals on each of those spots. Can you still see that? Yeah, you can. Okay. So that's how you find the height, right? So you just have your list of equations, and you have the list of variables you know. In this case, I knew Vy, I knew Vyi, I know G. So I look at my list of equations and see, oh, this equation does that. So I can use that equation. Will it always be the case that it's conveniently already solved for the variable you're looking for? No. Sometimes it might be that I know the maximum height and I need to find the initial y velocity or something like that. And so I'd have to do some algebra to solve for this. I strongly encourage you to do the algebra before you start plugging in numbers, but either way works. Okay. video is going way too long. I'm waffling. I'm losing your interest. So let's go on to time in the air. Let's say time in the air. So for time, there are a couple ways you could do this. You could find the time it takes it to go up and then just multiply by 2 because it's perfectly symmetrical given that we're ignoring air resistance. However, a better way, in my opinion, and by the way, if you were to do that, you would use this equation. So you know the final velocity in the y direction is going to be 0 because you're going to take the top as your final. Your initial is 86.6. You know g is 9.8. Solve for t. It'll be your only unknown. And of course that's t1/2, so you'd have to multiply by 2 because that's just the time it takes to get to the top. But a nicer way is, because we know this is a flat surface, it's launched from the same height at which it impacts, so we can say delta y is equal to 0. And we know, we want to know the time, we know vyi, we know g. I would use this equation right here. And this equation can be scary sometimes because it's a quadratic. But in this case, because delta y is 0, it's going to simplify real quick. So that's going to be equal to, that's going to be equal to negative 4.9, because 9.8 over 2, g over 2, t squared plus 86.6 t. Because this is all equal to 0, I can just move that over there and say 4.9 t squared is equal to 86.6 t. And oh my goodness, that t cancels out with the t squared there. And so now I just divide both sides by 4.9, and I get approximately 17 point, I went to tenths there. Going to hundredths of a second seems excessive, and it is excessive given our sig figs, but there we go. 17.67. If you're paying attention to sig figs, and this problem, this is a 2 to 3 sig fig problem, so you do probably 17.7 seconds is a little bit more appropriate. But generally in physics, we don't care that much about sig figs. In chemistry, chemistry teachers tend to harp on that a lot. In physics, it's not as big of a deal, typically speaking. In the courses, at least. When you're doing real research, it becomes a very big deal. Okay, and then part C. Now, by the way, if delta y is not equal to 0, like maybe this lands up on a cliff up here, so it hits there, or there's a up on a cliff, up on a ledge, or if it falls down a cliff, so it hits down here, then delta y is not 0. You're going to have to use a quadratic equation for this. And you cannot get away with saying, oh, I'll just go to the top and then multiply by 2. Because this is no longer just half the time. It's either going to take less time or more time. So you're going to end up using quadratic equation in that case. Or just graph it. Okay, now let's find, what else do we need to find? Range. Okay, so for this one, I left myself not very much room. In the solutions I gave you, I showed how to do this properly. But this video is already 14 minutes long. So I'm just going to jump straight to this special equation that in the solutions I gave you for the chapter 4 problems, I show how to do this properly, finding the time in the air and then using this. So like we now know the time, so we also know Vx, so we can find delta x. But what if you do that all using variables? Right now we could do that easily enough. Delta x is equal to the range, which is going to be equal to 50 times 17.67 times 50. We're going to get that looks like a greater than sign, approximately 884 meters. Or, I went to centimeters there, so 883.70 meters. That's easy peasy. But what if you, for whatever reason, don't have time? Or you want an equation to be able to jump straight to this. You don't want to have to find time first. Because maybe part B wasn't find time. Maybe this is part A. Well, if you are on a flat surface, again, if and only if you are on a flat surface, if you land on this ledge or cliff, this does not work. But if you're on a flat surface, there's a special equation called the range equation, and it's VI squared. This is not VYI or VXI, this is VI. So in our case, 100 meters per second times the sine of 2 theta. This, in the proof or in the work for this uses a trig identity, which I know you like a lot, divided by G. Notice that's just G. It's not negative G, it's just G. And so then we get 100 squared sine of 2 times 60 divided by 9.8, 100 squared. And like magic, we are going to get times 120, or sine of 120, the same answer we did before, divided by 9.8. We get the exact same thing. It's magic. 883.70 meters. So again, that only works if you're on a flat surface. Okay, so that is a very, that's my kind of first example problem for projectile motion. Real quick, what would happen if you go to the moon? G on the moon is equal to about G over 6. Typically when you just write G, by the way, that references G on Earth, but you can do that if you want to be very clear. So what would happen to all these things? Well, the height would, well, we have a over 6, that's a double denominator to come up on top, so you'd be multiplying by 6, so it would go 6 times as high. In this case, well, G is stuck in there, and it's linear, right? It's not squared. So you would get 6 times as much time. And now here in the range equation, G is also linear, so you'd go 6 times as far. Is it always 6 times? There are some situations when you might get a square root of 6 or something like that. Like the velocity at which you have to throw something to get the same height is only the square root of 6, or 1 divided by the square root of 6. But there you go. This has been too long. I hope that was helpful. Goodbye.